Hello, 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 hello. It's early morning here, I just woke up. Probably not early morning for you. Next problem. Definitely an easy problem. By the way, my apologies, I'm still wearing my yukata, which I often do in the morning when I just get out of bed. I like yukatas, by the way, I have several. I've been in Japan so many times, I bought every time another yukata. Okay, next problem. You may have been at amusement parks where they have rooms which are in the shape of a huge cylinder. So the walls of the room are a cylinder. And this whole room, they can spin around. People go in there, and then the room starts to spin around faster and faster and faster, and then there comes a moment that it spins fast enough that the floor on which the people stand can be moved downwards, away. So they're no longer standing on the floor, but they don't fall. They are still pushed against the outside walls, and they just hang there. I've done it once. It's actually very cute. Not a difficult problem. Let's look at my geometry. So this is a cylindrical room. The radius of this cylinder is 3 meters. And here is the floor that can be lowered on command. And so here's a person standing on that floor. The mass of that person is 70 kilograms. If you need it, we will all assume that the gravitational acceleration is 10 meters per second squared. So, the room is going to spin faster and faster and faster, and at a frequency of 0.65 Hertz, they lower the floor. And the person doesn't fall down. The person stays stuck to the wall. So the question now is, what is the minimum required friction coefficient between the wall here and the back of that person, so that the person doesn't slide down? That's question number 1. 3-digit precision is fine, SI units, okay? The question is, what is the acceleration that this person experiences at that frequency? Let's take the back of the person as the criterion. You should be able to calculate very easily that the linear speed of that person, just rounded off, not 3-digit precision for now, is about 44 kilometers per hour. So it's doable, but it's quite a speed. So I want to know now what is the acceleration that the person experiences, the back of the person, 3-digit precision, and the friction coefficient also 3-digit precision. And now comes the last question, and that is, suppose the room spins faster than 0.65 Hertz. Could the friction coefficient between the wall and the person now be lower than the value that you calculated? Or does it have to be higher than you calculated for the person not to slip down? Alright, yes, I agree, it's a high school problem. But one of the viewers asked me to do this problem, I forgot his name. And so I thought, well, yeah, it's perhaps a bit too simple, but nevertheless, high school problems occasionally are very nice. So, have a nice day. Take care, and of course we'll be friends. I'd like to add something to this problem. It's not a new question, but you may wonder whether this situation may be dangerous for that person. I did my checking on the web. Marginally dangerous. Marginally. And certainly if the frequency were to be increased quite a bit, it would be very dangerous. People would faint. Let me give you a little bit of a hint. If I had to do this problem again, I would have lowered this a little bit, but I'm not going to do that. Alright? So if you ever are in a situation like this in an amusement park, insist that the frequency is a little lower, or of course the radius could be different. That's a different story, of course. Alright? Take care.